Hello to you all. My name is PAPATSIAKMAKI, and I will present to you today a study of mine that took place during previous spring in order to look into the possible positive influence of using a specific digital educational program with students in 6th grade so as to enable them to deal better with geometric tasks concerning area and perimeter. Geometry is the key for the description and dealing with physical environment. Students use geometric models for mental depictions concerning reasoning of space that is developed through discovering, description, categorizing, organizing and calculating objects in space or on a simple piece of paper. For the completion of geometric problems, 3 cognitive operations are needed: visualization, constructive proceeds, reasoning. Students in 6th grade are considered to be mentally matured and trained enough so as to have constructed geometric concepts concerning identification and examination of several shapes, to have felt concepts like area and perimeter through their senses, to process complex and more abstract activities, and to be capable of practicing variously calculations using multiple instruments to solve problems associated with surface. Nevertheless, many students of different ages often encounter difficulties concerning area and perimeter. One common difficulty has to do with the misconception that shapes with the same or different area definitely have also the same or different perimeter respectively, and vice versa. For example, in this case, as it appears on the monitor, 100 children in different grades were presented with a rectangle and hexagon task related to the comparison of perimeters. Initially, 2 identical rectangles were presented. Then, a small square was removed from the corner of one rectangle, so it was formed as an hexagon with smaller area than the other rectangle's area, but their perimeters remained equal. At least 70% of the students in each grade level incorrectly claimed that the rectangle's perimeter was larger than hexagon's perimeter because the rectangle has more area or a corner was not taken away from it, and other similar arguments. Many other current studies have confirmed that this misconception actually concerns a large percentage of students in elementary school, high school, even in university. Several different approaches have been developed so as this difficulty is to be explained. One argues that incorrect responses result from lack of required cognitive schemata. In another point of view, these difficulties come up when is neglected or not handled appropriately the fact that students bring their own initial conceptions to learning situations that have constructed through their personal everyday experiences. In accordance with the third approach, these difficulties are associated with the interaction of 2 distinct types of reasoning processes: formal logical process and intuitive process, which does not always result in agreement, thus producing contradictory conclusions or misconceptions. These theories seem to be quite different, but with a closer look, common features between them can be revealed concerning educational framework and procedures. Namely, key feature in all cases is that students bring certain reasoning patterns that have to be taken into account during educational procedures in a way that students' thoughts will be the start and the base upon which the procedure will be formulated. This key feature is applicable in Van Hyl's theory, where flexible adaptation to students' level of thinking is the main educational strategy. In Van Hyl's model, there is an hierarchy about reasoning of space into 5 levels of understanding, depending on the reasoning processes that take place during exploration of geometric objects and the types of geometric ideas that are mentally processed for each of them. Therefore, educational activities are organized in a form of a sequence that enables students to go from one level to another, where each level essentially functions as an autonomous learning phase. They start from exploration phase by visualizing geometric ideas, which then analyze in the guided orientation phase. Then they are guided through explanations to assumptions and correlations that help them in the free orientation phase to approach geometric proofs, which are the condition for completion. Educational activities based on Van Hyl's theory seem to be managed on the part of students with greater ease and prove to be particularly effectual when they are organized within a technological framework like dynamic digital geometry applications. This is mainly due to the creative tooling dimension of these applications, as it is crucial to mediate the type of tool in introducing geometric concepts. Dynamic digital applications, among their other features, are an expedient instrument to introduce children to Van Hyl's first level of geometric thinking. By combining imaging with dynamic manipulation, children are led to the second level of Van Hyl. These applications offer endless possibilities for experimentation and self-action, for hypothesis and discovery of correlations that are in line with the third level, as well as for evidence on Van Hyl's fourth level. Tangible user interfaces, TUIs in short, are a kind of dynamic digital applications that seem to enhance learning and understanding of abstract phenomena. TUIs refer to the interaction of virtual or remote systems with the user, who is the recipient of bodily irritations that operate as feedback. Feedback is embodied by the user, who can act variously with respect to environmental objects. TUIs include an interaction device and a representation of the virtual environment that the user interacts with. TUIs provide children with a collaborative environment where knowledge is constructed by virtually playing. Learning in this case is the product of the connection and interaction of mind, physical action and representation, namely environment. Main advantage of TUIs is the combination of numerous stimuli and pedagogical support, along with keeping the user in engagement with real physical experiments. This advantage makes them capable of supporting cognitive functions and modeling ideas, assisted by the provision of multiple representations. Training with TUIs can take several forms, like per person, in pairs, or in small groups. On the basis of the aforementioned, an educational digital program named Ευκλήδιο Σχολή was designed using tangible learning through tactile interfaces within a dynamic environment, which was mixed reality because it framed digital representation with physical objects so as to be more realistic and to enhance sensitivistic learning by children. For this program, Scratch application was used in conjunction with Makey-Makey tools, through which tangible interface was made. A three-dimensional model of a garden was created, where activities took place through virtual representations projected on the surface of a maquette. Scenario concerned children visiting the Euclidean school, where they engaged in activities associated with concepts of area and perimeter. Construction of activities was carried out in accordance with Van Hyl's model, leading children gradually from visualization to guided orientation analysis, appropriately empowering them to hypothesize and to discover associations about geometric evidences. Selection of activities took into account typical learning readiness level of students in 6th grade. Appropriate forms of feedback were included as scaffolding to orient children's thinking through active exploratory learning at a subsequent learning level. As it appears on the monitor, educational environment evolved using a 1.5 meters plus 1 meter maquette where digital and playful realistic elements were combined. Total duration of training program was about 30 minutes, and it could be handled by children either per person or in small groups of 2 to 3 children without any external help, just by following interactively the scenario. Children were standing in front of the maquette, holding a special ring that activated the Makey-Makey system, so they could interact with what was projected on the surface of the maquette by tapping on various surfaces points. Children were introduced to the application by Arithmomnemon, a virtual hero who was supposed to be a Euclid's student. He initially presented children with a series of imagery activities where Kandinsky's paintings were used in order to be fulfilled Van Hale's theory first level of holistic recognition of shapes without qualities analysis. Then he introduced children to the second level of activity, the one of analysis, where they were asked to use terminology and qualities recognition without arguments about area and perimeter. During this phase, audiovisual amplifiers, indicators, and feedback elements were used whenever necessary, depending on children's learning readiness level, so as to help them construct further knowledge. On this basis, they were progressively led by Arithmomnemon to the third level of non-typical production, developing a more detailed perception and intuitive understanding of area and perimeter qualities, and reasonably arguing for the relations between them. Here children were asked to form the garden in a variety of ways through which dimensions of area and perimeter were affected. For example, children had to judge whether garden's perimeter had changed by adding a tap to a corner, or to judge whether the area of a specific part of the surface where spruce were planted had changed because of the differentiation of its shape. Various computations were made on the part of children by measuring the squares or by using a rope following digital audiovisual feedback. In final phase, naming the fourth level of production, children were asked to demonstrate the independent relation between perimeter and area, making further adjustments to the elements of the garden. Fifth and final level of Van Hale's theory was not included in this program because it shoots for the higher mathematic level of thinking of adults. The purpose of the study concerned whether an educational program of this type would improve students' performance as far as computations, conceptual understanding, and visual sensitization concerns in geometric tasks associated with area and perimeter. 30 students in 6th grade attending public elementary schools in Western Macedonia participated voluntarily. A non-formal pre- and post-test formed as multiple-choice test was used, containing 12 activities concerning computation, conceptual understanding, and visual sensitization for area and perimeter. Activities content was different between pre- and post-test, but in each case, activities were organized with the same order and in correspondence as far as the examined quality of each activity concerns. Initially, students completed the pre-test, then they used the digital program, and afterwards they completed the post-test. For data analysis, the non-parametric Wilcoxon test was used because variables did not follow normal distribution. Theoretical but not practical interpretation of perimeters and areas definition, all types of computations except computations concerning perimeter with emphasis to measurement units of a square, and visual sensitization of area concept on the basis of net of a square were the variables in which there was statistically significant difference between students' initial and final scores. Students improved their overall performance drastically. Their post-test score was nearly doubled, and 27 students gave more accurate answers. Also, students' computations were improved since after the program, 1 out of 3 gave the most correct answers. There were significant differences as far as conceptual understanding and visual sensitization concerns, since 22 and 16 students respectively gave more correct answers after the program. In conclusion, a tangible user interface program of this type, designed on the base of Van Hale's theory, seems appropriate and effective for students in 6th grade. By the use of the proposed application, common misconceptions about area and perimeter can be handled effectively as long as particular technological means are properly exploited. These findings can lead to new educational paths concerning educational tools that are commonly used in a classroom, offering an opportunity to all students construct concepts of area and perimeter according to their learning readiness level. Of course, these findings need support through further research in this field. Thank you very much.